Let's pick this lecture up having to do with sequences where we left off. Where we left off was talking about how we can graphically look at sequences, where we're graphing the position number on the x-axis and the value of the sequence on the y-axis. We found that using parametric mode that we can graph them relatively easily, and that's great if our definition of our sequence is explicitly defined. You're going to remember an explicit definition for a sequence kind of looks like this. Oh, the sequence a sub n is 5 plus n minus 1 times 3. That's an explicit definition. You give me an n, the position number, I'll give you back the sequence's value at that position. That's explicitly defined. And this is an arithmetic sequence. Well spotted. I could also explicitly define a geometric series. And that's all great. But what happens if we want to define a sequence recursively? Well, the calculator is actually built in a way that we can do that as well. We can graph the recursively defined function in the calculator. You just got to know where the new stuff is. So let's start with, we're going to move out of parametric mode where we were last time, and we're going to move into sequence mode. The fourth of those four options, function, parametric, polar, sequence. And again, continue to be in dot mode as compared to connected mode. Everyone get to the modes and make those changes if you please. If you don't have a calculator, I have some extras. I have 4 extra. Anyone need them? Now, once we do that, our y equals menu looks different. We are no longer defining what y is equal to, or what y and x were equal to like we did in parametric mode, but rather we're defining elements of the sequence. For example, n min. Remember, n is the letter that we use to describe position in the sequence. We're saying that our sequence starts with position 1. By the way, many mathematicians like to start their sequences actually at position 0. So they give you the option. Let's start our sequence at position 1 because that's the number that was given there. And then it says, well, what on this third line, what do you want the sequence to have as its first value? So between the first and the third, we have essentially taken care of that fact. Our starting position is position 1. Our starting value at position 1 is 4. Now, we can go and we can type this in. All right? Now, where are we going to find the u value and the squiggly n value? Well, remember that the button on your calculator that starts with x and then goes to t and then goes to theta and then ends in n, well, that's where you're going to get your squiggly n. You're going to get your squiggly n from that button, which changes based on the value. Where are you going to get the little u? And the answer is the little u is right above the 7 key. So it's second 7. Okay. So when you're in function mode, it's an x. When you're in parametric mode, it's a t. When you're in polar mode, it's a theta. And when you're in sequence mode, that one button is an n.
Over there.
Yes?
So the B that we see in our book is represented by U on the calculator?
Yep.
And then how does it know, because like right now we're doing U times n minus 1?
No. That's not u times. That's of n minus 1.
How does it know?
Okay, this expression that I'm circling in blue here is equivalent to this expression there. The u is acting like the name of our sequence. In this case, b. So b and u match up. And this subscript, n minus 1, is the argument inside that u. So is that u times n minus 1? It's saying, what is the value of u, our sequence, at position n minus 1, the previous position. All right? Now, after we get those three pieces of information in, where are we starting? What's the starting value? And then how do we define all the other values in our sequence? Then, oh, look at me. So here's the reminders. Where do you find the u? It's above 7. Where do you find the n? It's on there. Look at that. That's so helpful. All right. What's that? I thought that was really well done. It was really hitting stride there. Okay, put that away. All right. Then the last thing, if we want to do the graph, we need to say, okay, what's our window going to look like? Remember, our horizontal axis is going to be representative of the n values. 1, 2, 3, 4, so on and so forth. So the question is, where are we going to start? Let's do the first 10 terms. Also, when we're graphing, what are the x values and the range of x values and range of y values that we're going to want to make sure that the screen, the dots can be seen. For example, this looks to me like this is going to be an arithmetic sequence. It's going to be 4, and then the second position is going to be 4 plus 2. 6, and then the third position is going to be 8. So if we go through these 10s, it sounds like we're going to go through 4 through 14. So we better make sure that our range of y values can capture that. So I put in negative 5 to 25. And when all is said and done, we get all of those things in the calculator all nice and spiffy. There is indeed the graph of that arithmetic sequence. And if you go into trace mode, every single dot has its sequence position number, the value of x, and the value of y. And again, x and n should be the same value, I believe. To tell you the truth, I have not used this graphing mode very often. I taught the first 7 years of calculus without ever doing this. You're getting good stuff. All right. So, there we have it. Graphing sequences using sequence mode. Any questions about that?
So why is your A sub n?
Why is my a sub n?
Or no?
Let me back out. We're
I thought A sub n was like a generic.
a sub n, b sub n, c sub n. They're all generic names for different sequences.
So B
Sorry. Yeah. Go ahead.
So your y is your B sub n?
Mm-hmm.
So and then is your x. So whatever your n is.
My n and my x are the same thing, and now this is 4 units. This one is 4 units above y. This one's 6 units above y. 8 units above y.
So B sub 3 equals 8.
B sub 3 is equal to 8, right? All right. Okay. Now, I'm so glad we got all of that done, because now we can get to the calculus part. We say that sequences may or may not have limits. Now, this definition is the very, very rigorous mathematical definition of a limit. If you say that that sequence approaches some particular value as n approaches infinity, what you're saying is that it gets closer and closer to that value. How close? Well, the mathematicians like to define it it says if you think the limit approaches the limit L, that means it doesn't necessarily reach L, but it gets closer and closer to L. How close does it get to L? Well, we developed this new little symbol here, and that thing that looks like an E is pronounced epsilon. And we say that if you truly think that a sequence gets close to L, that means if you give me an epsilon, I have to tell you how big of an N you have to go to get that within that boundary. You say that this limit goes to a particular value. Well, here's that limit that you say it's going to. Epsilon represents a range of values around L. And if it really does go to that limit, I can just tell you, when you get up to 100, you're within an epsilon of L. Yes?
So, I'm assuming the limit can only work with geometry.
Well, certainly you recognize that arithmetic sequences do not hone in into a particular value unless the common difference is 0. You're absolutely right. And indeed, certain geometric sequences, do indeed hone into a particular value. For example, here's a geometric sequence. Are you ready? Are you ready? 1 is my starting value. 1/2 is my second value. 1/4 is my third value. What's my common ratio in this geometric sequence? 1/2. Because if I take 1/4, I multiply it 1/2, I go to 1/8, and then a 16th, and then a 32nd. And as I develop this particular geometric sequence, all those numbers are getting closer and closer to 0. That particular geometric sequence, the limit as n approaches infinity is 0. Now, does the sequence actually reach 0? No, it gets closer and closer. But if you said, Charlie, you have to get within 100. You got to get 100th of a 0. Let's see. I was at 1/4. That's not far enough. 1/8 is the next one. That's not within 100. 16th? 16th? I don't know. Is a 16th within 1/100th of 0? No. I think I have to go to 1/128. Which is 2 to the 7th.
So 1/2 plus 1.
Okay, so I say as soon as I get to the 7th thing in that sequence, I'm within 1/100th of that goal. If I try to do that to a number that isn't really the limit, it won't work. So when I'm actually approaching the limit, I can just say, oh, if I get to 7, I'm within 100th of that limit. Of course, Charlie being the jerk that he is, he says, no, I didn't say 100, I said 100,000. In which case, I probably have to have a bigger N to get within that close. But if it's truly that limit, I'll get within that close. I'll get within that epsilon of the limit. All right, I cannot believe that we have not yet finished this. I am going to say that even though we haven't finished it, come on, you still have the ability to do this work. And you should get probably at least